You know that feeling, right? Stepping outside on a warm day and feeling that perfect cooling breeze wash over you.
Hmm.
Or maybe the opposite, being stuck in a stuffy room, wishing for just a breath of fresh air.
Yeah, definitely know that feeling.
That simple sensation, air moving around you, it feels so natural, so intuitive. But behind it is this, well, this fascinating world, a deep blend of complex physics and ancient, almost forgotten wisdom.
Absolutely. It's far more than just, cracking open a window. It's really about intentionally shaping the spaces we inhabit, designing buildings not just to stand up to the elements, but to work with them,
Hmm.
to actively harness natural airflow.
And that's exactly what we're diving into today. Welcome to this deep dive where we're going to unpack the secrets, the art, and the science of natural ventilation.
Oh, great.
Our source material for this journey is a truly rich guide that beautifully bridges the worlds of architecture and science.
It really does. It pulls together threads from so many different areas: history, physics, the sort of invisible forces,
Hmm.
architectural traditions spanning centuries, modern design, and even the very personal human experience of feeling comfortable.
So, our mission today is to navigate this material.
Yeah.
We want to pull out the core principles, understand the crucial historical context, see how it's applied in modern buildings, and yes, even get a grasp on the basic physics that makes it all possible.
Kind of demystify it a bit.
Exactly. The goal is to give you a well-informed perspective on how buildings can breathe naturally and why that matters so much. Okay, let's unpack this.
Right. Let's start by looking at why buildings need to read in the first place,
Yeah.
and maybe how, for a while there, we kind of lost our way in making that happen naturally.
Good starting point. Think about life before mechanical systems were commonplace, before air conditioning was everywhere.
Well,
The need for fresh air wasn't just a matter of casual comfort, it was seen as absolutely vital for public health. Physicians, public health specialists, they were raising concerns about air quality in crowded indoor spaces way back, as early as the 17th century.
yeah, especially as institutions like schools and hospitals started bringing more and more people together indoors.
Exactly. Density.
And the source uses this really evocative description, saying buildings sweat, age, excrete, and they respire.
Huh, that's quite an image.
It is, isn't it?
Yeah.
It's a powerful way to think about them not as static boxes, but as dynamic entities interacting with their environment. And the air inside is definitely dynamic. It's filled with things off-gassing from the building materials themselves.
Like paints or carpets.
Right, all that stuff. Plus all the odors and carbon dioxide from us, the occupants, just by being inside and breathing.
So getting that stale, potentially unhealthy air out and bringing fresh air in was a constant challenge and really a major focus back then.
It really ramped up in the early 20th century, didn't it? Driven by that strong belief that fresh air was the best medicine, particularly for diseases like tuberculosis,
Oh, absolutely. TD was understood to be spread through the air, often flourishing in dense, poorly ventilated urban conditions.
which led to this push to build sanatoriums, specifically in locations renowned for their pure air, often high up in places like the Swiss Alps.
Like in Davos, if you've ever read Thomas Mann's novel, The Magic Mountain, that whole story is set in a TB sanatorium there. It really highlights this era and this belief.
Exactly, and you see this belief directly shaping the architecture of the time. Alvar Aalto's Paimio Sanatorium in Finland, built in the 1930s, is a perfect example.
Right. Its location was chosen precisely for the clean forest air.
And Aalto designed the building itself to be part of the therapy. It had these large open balconies so patients could be exposed to the air for healing. Even the window details were ingenious.
How so?
Well, they had two panes of glass, creating a small cavity that would gently pre-warm incoming air before it entered the patient rooms, made the fresh air less shocking in the cold Finnish climate. What's so insightful here is how architecture itself became a key therapeutic tool, directly leveraging the environment.
That's a powerful idea, the building as healer. But then as we moved into the mid 20th century, there was a big shift. The rise of mechanical systems, especially air conditioning, became the dominant force.
Yes, the goal became achieving homogeneous and constant interior thermal conditions. That idea of perfect uniform temperature and air quality 2047 regardless of what was happening outside.
This chase for predictability led to a whole new kind of building design, didn't it?
It really did.
A design where, in many office buildings, the windows didn't even open.
Right. Why bother with the messy, unpredictable reality of natural wind and temperature when a machine could deliver exact air as figures like Le Corbusier envisioned for his ideal cities?
He had that famous line, didn't he? Something like, a window is to give light, not to ventilate.
To ventilate, we use machines. It is mechanics. It is physics. That was his thinking.
But the real irony, though, is that by sealing up buildings and relying only on machines, the exact opposite of perfect health and comfort often happened.
That's so true. Indoor air quality frequently worsened, leading to significant problems like sick building syndrome and other illnesses linked directly to the building environment.
We essentially sealed ourselves off from the natural world with consequences not just for our comfort, but for our health and obviously our energy use.
It's a classic unintended consequence, isn't it? The technology meant to solve a problem ended up creating new ones.
But fortunately, with rising concerns about energy consumption, climate change, resource use, there's a major revival happening now.
Absolutely. Designers and researchers are looking back at those traditional climate-responsive strategies. Natural ventilation isn't just a historical curiosity anymore. It's seen as a vital, sustainable approach for contemporary design.
And this history matters to you, the listener, because the buildings you likely spend your days in were shaped by this journey away from and now back towards natural ventilation. Understanding those past mistakes and the potential benefits highlights why bringing natural airflow back into design is so important for health, comfort, and the planet.
Definite. Now, to really understand how natural ventilation works, we probably need to touch on some basic physics, the invisible forces that move air.
Right. But don't worry, no advanced degrees needed. Huh. No, definitely not. Just enough to appreciate what's happening. Air has fundamental properties: temperature, pressure, volume, density. They're all interconnected, right?
Like the ideal gas law connects them. You change the temperature, you change the density, which affects the pressure, and so on. Think about heating air, it expands, becomes lighter, less dense.
And when we talk about air moving and changing temperature, we're really talking about energy transfer. The first law of thermodynamics: energy can't just disappear. It moves or changes form, like heat transferring from a warm object to a cooler one. Simple enough. There's also the simple idea of mass conservation.
Right, the amount of air stays constant. So if you push air through a smaller opening, it has to speed up to get the same amount of air through in the same time.
It's like putting your thumb over the end of a garden hose. The water sprays out faster. Same idea for air moving through building openings.
hmm And air particles themselves are subject to forces. There are surface forces, like pressure and viscosity, but the one that's really key for natural ventilation is a body force: gravity.
Gravity, how does that work with air?
Well, because warmer air is less dense than cooler air, gravity pulls harder on the cooler, denser air. It essentially sinks, lifting the warmer, lighter air upwards. This difference creates buoyancy, and that's the engine behind the stack effect we'll talk more about.
Ah, okay, that makes sense. Buoyancy.
We also need to think about how air flows. Sometimes it's smooth and orderly, what we call laminar flow, particularly very close to surfaces. There's this no-slip boundary condition where particles basically stick right at the edge.
But that's not usually what's happening in a room, is it?
Not really. More often, especially in buildings or out in the environment, airflow is turbulent.
Yeah.
It's chaotic, swirling, mixing, creating eddies and vortices around obstacles like walls or furniture.
Turbulent flow sounds messy.
It is messy, but that mixing action is actually great for air quality. It helps distribute fresh air and dilute pollutants much more effectively throughout a space.
Okay, so turbulence isn't all bad.
Not at all. The downside is that turbulent air also transfers heat more effectively, which means spaces can cool down more rapidly if it's cold outside, or maybe more relevantly, feel cooler due to that air movement even at the same air temperature.
Got it. And there's one more crucial principle about airspeed and pressure, right? Often linked to Bernoulli.
Yes, Bernoulli's principle, named after Daniel Bernoulli back in the 1730s. Generally for ideal fluid flow, where air speeds up, the pressure drops.
And that happens around buildings.
Absolutely. As wind flows around and over a building, it speeds up in certain places, creating areas of lower pressure, especially on the downwind side, the leeward side. And you get higher pressure on the upwind or windward side, where the wind is hitting directly.
Okay, so understanding these basic ideas, how temperature affects density and creates buoyancy, how air speeds up through smaller openings, and how pressure differences are created by wind flow helps us understand the two main drivers of natural ventilation.
Exactly. First, there's wind. Wind is essentially air moving from high-pressure areas to low-pressure areas. On a massive scale, this is driven by things like the Earth's rotation and uneven heating by the sun, creating large atmospheric motions.
But closer to the ground, where our buildings are.
Closer to the ground, it's heavily influenced by obstacles, landforms, trees, other buildings, All these create friction and turbulence, complex patterns, especially near the surface. So predicting wind often involves looking at long-term patterns for a specific location.
Okay, so wind is driver number one. What's number two?
The stack effect, powered by temperature differences in buoyancy.
The warm air rising thing.
Precisely. Warmer, less dense air rises. In a building, warm indoor air rises through vertical spaces, like stairwells or atria or shafts. This creates lower pressure at the bottom of the space and higher pressure at the top, relative to the outside.
Like a natural pump.
Exactly like a natural pump. It pulls cooler outside air in through lower openings and pushes warm air out through higher openings. There's usually a point somewhere in the middle called the neutral plane, where the pressure inside matches the outside, where the forces balance.
You can feel these forces every day, can't you? The pressure of wind pushing against you, or a building wall that's one force,
Hmm.
and feeling warm air collecting near the ceiling or rising up a stairwell. That's the stack effect, powered by buoyancy.
Understanding these basic physics principles moves us from just, opening a window and hoping for the best to intentionally designing spaces that collaborate with these natural forces. It gives us the why.
And where your building is located makes a huge difference to those forces, doesn't it?
Oh, fundamentally. This brings us to location, 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 climate, and topography.
Right. The long-term patterns of weather define a climate zone. Systems like the Köppen-Geiger classification, which is surprisingly old, dating back to the late 19th century.
Yeah, developed by Vladimir Köppen, based on vegetation, temperature, precipitation.
It divides the world into different climate types. And the potential for effective natural ventilation varies enormously depending on your climate. Some places have consistent breezes, others rely more on temperature differences for stack effect, and some have challenging humidity or periods of stillness.
And a really fascinating tool for understanding the wind patterns in a specific location is the wind rose. The source material dives into the surprising history of this simple diagram.
It's not just a modern weather chart thing.
Not at all. It's much older than you guess, dating back to antiquity. People have been trying to map and understand wind directions for millennia. Think about it. Wind was crucial for sailing, for agriculture.
Makes sense.
In ancient times, winds were often seen as powerful, almost personified entities, like the Greek wind gods, Boreas, Zephyrus, Nodos, Eurus, mentioned in Homer's Odyssey, each tied to a direction.
And Vitruvius, the Roman architect, apparently cataloged a whole bunch of distinct winds.
She did, mentioning up to 24. This practice of mapping and naming winds carried through history. Hildegard of Bingen in the Middle Ages interpreted natural science, including winds. It evolved into the modern wind rose diagram we see today, which really originated in the Renaissance.
So the circle diagram with the lines showing direction and strength.
That's the one. A circle showing direction, with lines or colored segments indicating how often the wind blows from a certain direction and how strong it typically is. You can find wind roses for specific cities or sites, and they are still used today in design software like Climate Consultant to understand the dominant wind patterns. It's a different notation from the simple arrows showing velocity we often see now, which came later in the 19th century. You even see wind gods depicted in Renaissance art, like Botticelli's Birth of Venus.
Wow, okay. So wind roses have deep roots.
Very deep. And beyond large-scale climate and wind patterns, local topography matters hugely. Hills, valleys, large bodies of water, they create localized wind systems.
Like sea breezes.
Exactly. Sea-land breezes or mountain valley breezes. They're driven by temperature differences between the land and water, or between mountain slopes heating up faster than valleys. Even smaller differences, like between an urban area and surrounding rural land, or a forest and open grassland, can generate localized breezes.
And the shape of the land influences the flow, too.
Definitely. Moderate hills might just gently shift wind direction, but steep changes in elevation, like cliffs or sharp ridges, can create chaotic, swirling air patterns, eddies, and turbulence.
Then you put a building on this landscape.
And it immediately becomes a significant obstacle in that airflow. The air has to go somewhere either around the building or, if you design it right, through the building.
So the building itself changes the local wind pattern.
Yes. Its shape, its height, how it's oriented relative to the wind and sun, where it sits in relation to the terrain and surrounding buildings, all of this influences how wind flows around and potentially through it.
And the resistance created by the building form and its openings is what generates the pressure differences needed to drive air through the intended ventilation paths, right?
Precisely. You're manipulating the pressure field around the building with its shape and openings to encourage flow along a desired path.
So, understanding your local climate, looking at a windrows for your specific area, like the example shown in the source for Chicago or Mumbai or Frankfurt, and considering the immediate topography around your site are crucial first steps. The building needs to be specifically tuned to its place.
Absolutely essential. And if that place happens to be a city, things get even more complicated.
Right. The urban challenge.
Absolutely. Urban environments create unique microclimates. There's the well-known urban heat island effect. Cities tend to be warmer than the surrounding rural areas, especially at night.
Because of all the concrete and asphalt soaking up heat.
Exactly. Materials, color, reflectivity all play a role. And the dense collection of buildings dramatically changes how air moves. Instead of a relatively open flow, you get these complex patterns within what are called street canyons.
The spaces between buildings lining a street.
Right. Airflow in these canyons is largely influenced by the wind blowing above the buildings,
Mm-hmm.
above the urban canopy layer. And depending on the wind direction relative to the street, is it blowing straight down the street, parallel, straight across it, perpendicular, or at an odd angle? You get different, quite complex flow patterns within the canyon itself.
Like little eddies and swirls trapped between buildings.
Yes, and secondary flows. The source mentions different regimes based on building spacing and wind. Skimming flow, where wind mostly blows over the tops of closely packed buildings. Wake interference, where the turbulent zones behind buildings interact. And isolated roughness flow, when buildings are farther apart and act more like individual obstacles.
Sounds really complex to predict.
It is. And it makes designing for urban airflow tricky. Because the wind direction and these street canyon effects are constantly shifting, ventilation openings in urban buildings often need to be designed to function as both inlets and outlets, depending on the conditions at that moment.
So they can catch airflow whenever and however it presents itself.
Exactly, and account for potential flow reversals within the canyon.
Hmm.
Getting precise, site-specific wind data within a complex urban canyon can also be challenging, precisely because the airflow is so turbulent and unpredictable down at street level.
So living or working in a city means you're interacting with these unique urban airflow challenges and opportunities every day. The familiar shape of the street you're on directly impacts how air moves around you in surprisingly complex ways you might not even notice.
Definitely. Given all these forces and complexities, how have people throughout history and today actually built spaces that successfully harness natural airflow? This gets us into some fascinating architectural history.
Right. Learning from the past, exploring architectural archetypes. The source emphasizes the value of what's called vernacular architecture.
These are the traditional, often anonymous building styles developed over generations in response to local climate and available materials, before the era of widespread industrialization and mechanical systems.
Like indigenous building traditions.
Exactly. These traditions are a treasure trove of climate-responsive design ideas. Think of it as inherited wisdom, refined through centuries of trial and error. Figures like Lukács refer to these as mind models or architectural archetypes, and Bernard Rudofsky celebrated them in his famous book and exhibition, Architecture Without Architects.
They offer time-tested solutions tuned to specific environmental conditions.
Precisely. Let's look at some of these spatial archetypes, specifically for ventilation, as the source outlines them. First, the simplest, the cave.
Okay, going way back.
Way back. Caves naturally utilize geothermal cooling, the Keber, the stable temperature of the Earth, and temperature-induced pressure differences. If the outside air is hotter, the cooler, denser cave air can create a natural pressure differential, drawing in warmer outside air, which is then cooled by contact with the cave surfaces, creating a subtle airflow.
Like natural air conditioning.
In a very basic sense, yes. The kiva spaces of the ancient Anasazi people in the American Southwest are mentioned as using this principle.
Okay, what's next? The courtyard.
The courtyard, a typology found in warm and temperate climates all across the world. It's incredibly versatile.
How does it work for ventilation?
Well, in cooler climates, it can offer shelter from harsh winds, creating a protected microclimate. But in warmer climates, courtyards are brilliant for ventilation. They provide shade, often incorporate water features for evaporative cooling, and crucially, they act as central thermal engines.
Thermal engine.
Yeah, the often warmer air in the sunlit or partially shaded courtyard tends to rise. This draws cooler air from the surrounding shaded rooms through the circulation spaces like hallways or loggias and out into the courtyard, creating a natural airflow loop. The Palazzo Medici Riccardi in Florence is a classic example.
Ah, I can picture that.
Alvar Aalto also drew inspiration from traditional Finnish farmstead courtyards in his designs. And interestingly, even modern double-skin facades use a similar principle, creating a buffered thermal zone that can help drive ventilation.
Fascinating connection. Okay, what about the chimney?
While we think of them mainly for smoke exhaust from fires, the basic vertical shaft is inherently designed for stack ventilation. Hot air and smoke rise, drawing in combustion air from below.
But even without a fire.
Even without a fire, the principle works. Tall vertical spaces naturally encourage stack effect if there's a temperature difference. Think of steep roofs in hot, humid climates, like those found in palaces in Goa, India. They enhance the stack effect, allowing hot, humid air to rise and escape at the peak. Fireplaces were just early integrated spatial components that relied on and reinforced this natural vertical airflow.
Got it. Then there are those in-between spaces, passages, arcades, loges.
Yes, these are crucial transitional zones, thresholds between fully inside and fully outside. They're not fully enclosed, but offer protection from sun or rain while ensuring airflow.
Like a covered walkway.
Exactly.
Wow.
Covered streets in places like Jerusalem or Brussels provide shaded walkways that still allow breezes to pass through. Arcades, like those famous ones in Bologna, Italy, offer sheltered public space connected to the street, often used for shops and trade, facilitating airflow along the building edge.
And loges.
Loggias are essentially covered outdoor rooms or deep balconies. They offer breezy retreats from heat, very common in Mediterranean climates. Think of those famous examples by Michelangelo and Borromini overlooking the Tiber River in Rome. They act like horizontal wind catchers, scooping up breezes and directing them towards adjacent interior spaces.
They sound delightful.
They often are. And traditional windows could be complex systems too. The source mentions multifunctional Roman windows at Palazzo Cenci that combined layers, external shading louvers, operable glass windows, and interior shutters, offering really fine control over light, view, and airflow.
Amazing level of detail. And finally, the iconic wind catcher, sometimes called a basket.
Yes, the Melkoff or badger in Middle Eastern architecture. These are vertical towers, often quite sculptural, designed explicitly to capture prevailing winds high above the roofline and channel them down into the building interiors.
How do they work?
They're traditionally built from materials like mud brick and have internal chambers and vents oriented towards the dominant wind directions. The captured air is directed down, often into courtyards or main living spaces. They were highly effective at creating thermal comfort, partly by increasing air movement, which promotes evaporative cooling, helping people feel comfortable by allowing sweat to evaporate, especially effective in dry climates.
And people still use them.
They do. Reports, like one cited by Sue Rove, confirm they are still used and occupants find them comfortable. The Habitat Research and Development Center in Namibia is a great contemporary example using modern wind towers based on this ancient technology.
It's remarkable how sophisticated these traditional vernacular designs were, developed purely through observation and necessity over centuries without complex calculation tools.
Absolutely. And it's interesting that architects of the modern movement, while often focused on new technologies and aesthetics, were also clearly influenced by these traditions, even if implicitly. Le Corbusier's travel sketches, Alto referencing Karelian farmsteads, Frank Lloyd Wright's focus on the hearth as a central element. These show an underlying connection.
Though climate response wasn't always their main driver then.
Not always the primary focus, no. But these archetypes are now being actively rediscovered, reevaluated, and researched in sustainable and green architecture today. Teams are using modern tools like CFD, which we'll discuss later, to verify their performance and adapt them for contemporary use.
These ancient building types hold timeless lessons, don't they? They show us that sophisticated natural ventilation isn't some radical new invention. It's really a rediscovery, an art rooted in deep historical knowledge about living in harmony with climate.
Well said. And that historical knowledge, combined with modern science, is informing how architects design buildings today, actively integrating strategies for natural airflow right from the very beginning of the design process.
And that seems key. Natural ventilation isn't just an afterthought, like adding a vent here or there.
Absolutely not. It has to be fundamental to the architectural concept. The entire design team, architects, engineers, needs to think about how the building will interact with the dynamic outside conditions throughout the year. Cooling needs in summer, minimizing unwanted drafts and heat loss in winter, using free ventilation in the milder spring and fall shoulder seasons.
And they have to ensure the design allows the necessary volume of air to move through the building, using only the natural pressures provided by wind and temperature differences, right? You're shaping the building to work with the available forces, not overpower them.
Exactly. The source outlines the main ways designers guide air through a building, essentially defining different airflow paths.
What's the most common or effective?
The most effective approach is typically cross-ventilation. This is path one. Air enters on one side of the building, usually the windward side, experiencing higher pressure.
Where the wind hits.
Right. It flows through the occupied space and then exits on another side, which is often the leeward side, experiencing lower pressure or perhaps connected to a vertical shaft, creating a stack effect draw. It works best logically with openings on opposite walls or openings connected by clear paths like atria or stairwells.
The source mentions a couple of examples. Casa ad appartamenti Giuliani Frigerio.
Yes, as an early example illustrating how the spatial composition, the layout of rooms and openings, can facilitate cross-ventilation. But a really iconic case study is the Kanchenjunga apartment building, designed by Charles Correa in Mumbai, India.
Mumbai, that's a challenging climate, isn't it? Hot, humid, tropical.
Extremely challenging. The prevailing winds are strong coming off the Arabian Sea, especially during the very humid monsoon season. Just opening a window might bring in humid air without much cooling effect.
So what did Korea do?
His solution is brilliant and visually striking. The corners of the apartment block are carved out to these huge, double-height open loggias. These aren't just decorative balconies, they act as massive scoops or buffers.
Scoops for the wind?
In a way, yes. They modulate the strong incoming monsoon winds, breaking their force a bit, but also helping create the pressure difference needed to pull air through the apartments, providing airflow even in that humid context. It's a design tailored precisely to the local conditions.
That's fantastic. Any other cross-ventilation examples?
The San Francisco Federal Building by Morphosis is mentioned as using cross-ventilation as part of a mixed-mode strategy. That means it combines natural ventilation with mechanical systems, using the natural option whenever conditions are favorable. It relies on occupants being able to open windows and uses external solar screens.
Okay, so cross-ventilation is path 1. What's path 2?
Path 2 is single-sided ventilation.
Air in and out the same side.
Exactly. Air enters and exits through openings on the same facade. It's generally less effective for ventilating deep rooms because it relies more on wind turbulence near the facade and smaller pressure fluctuations or buoyancy effects within the room itself. It doesn't typically provide that deep sweeping airflow that cross-ventilation can.
But it's still used.
Oh yes, often necessary in buildings where you can't have openings on opposite sides, like cellular offices along a corridor. The Commerzbank Tower by Sir Norman Foster in Frankfurt is presented as a major case study that uses single-sided ventilation effectively, but alongside other larger-scale strategies.
Frankfurt, that's a milder climate, temperate but maybe less predictable wind.
Right, mild temperate with diverse prevailing wind directions. This building is really a masterclass in integrating strategies at different scales. It's a tall tower, so it's dealing with that urban canyon context we talked about.
So what's the strategy?
On a macro scale, it uses a huge central atrium that runs the height of the building and these large sky gardens like multi-story voids arranged in a spiral up the building. These gardens act like giant lungs.
Lungs?
Yeah, they enable both large-scale stack effect, warm air rising in the central atrium draws air from the gardens, and cross-ventilation across the building's triangular floor plan, because the gardens spiral up the building facing different directions.
Ah, so there's always a garden facing some direction that can catch the prevailing wind.
Precisely. It's incredibly clever. The building form itself is designed to adapt and capture wind from any major direction. Then, the individual office spaces adjacent to the facade also use single-sided ventilation, either venting directly outside or into the atrium or the sky gardens.
And this worked well.
Extremely well. There was a beneficial overlap between the natural ventilation strategy and the daylighting strategy, bringing light deep into the building via the atrium and gardens. This resulted in significant electricity savings. The performance data is impressive. Natural ventilation was usable about 85% of the year, much higher than the 60% they initially anticipated. And the building has run on 100% renewable energy since 2008.
That's a great success story. Let's look more closely now at designing specifically for stack ventilation, relying on that vertical airflow.
Okay. The Harm A. Weber Academic Center at Judson University in Elgin, Illinois is given as a good example here. This is a 4-story academic building.
What's its strategy?
It uses prominent wind catcher towers. But interestingly, they're designed specifically for cooling in summer, primarily driven by stack effect, not just wind capture. This is combined with regular operable windows that occupants can use for general comfort ventilation at other times of the year.
So the towers are mostly for hot weather?
Primarily, yes. The overall design is open plan internally to allow air to move easily towards the towers. They also incorporated elements to enhance the strategy, like exposed concrete slabs for thermal mass to absorb heat during the day.
We'll talk more about thermal mass later.
Definitely. They also have exterior wall extensions that house the ventilation stacks, and these double as daylighting features, splaying light into the rooms. And, quite cleverly, they put photovoltaic panels on top of the stacks.
Way there.
Besides generating electricity, the heat generated by the PV panels slightly warms the air at the very top of the stack, which can potentially enhance the stack effect by increasing the temperature difference between the top and bottom, strengthening the upward draw.
That is clever. Multifunctional.
Very. The building is also oriented perpendicular to the prevailing winds, which might assist airflow into the building, but the tower's primary function relies on the stack effect. An interior courtyard also contributes, acting as another pathway for air circulation and bringing in daylight.
This idea of connecting spaces to encourage airflow leads to the concept of free flow open space mentioned in the source. How is that different from just an open plan?
It's contrasted with the modern movement's free plan. While the classic free plan, often associated with glass block architecture, created visual connections, it often achieved this by sealing the building envelope off from the climate. Remember Le Corbusier, windows for light, machines for air. Beatrix Calmia argued this displaced the human subject from experiencing environmental forces.
Okay, so free flow is different.
Free flow is more about designing for spatial continuity and air movement in 3 dimensions. It's about intentionally using wall openings, passages, open stairways, double height spaces, galleries, courtyards, elements that connect different zones and blur the boundaries between rooms and even between inside and outside.
Creating pathways.
Exactly. It creates these intermediate zones of partial enclosure that belong to multiple spaces, offering multiple paths for air, light, and people to move through. It's a way of thinking about space that's inherently focused on flow and connection to the environment.
And the building skin itself, the facade, is becoming much more sophisticated in how it handles ventilation, isn't it?
Hugely so. Double-skin facades are a key innovation, especially useful in challenging locations, noisy urban sites, tall buildings exposed to high winds, or coastal areas with salt spray.
What are the benefits?
The air cavity between the inner and outer layers acts as a buffer. It provides acoustic insulation from outside noise, can enhance security, and critically for ventilation, it can slow down the external wind velocity before the air enters the interior inlet. This makes the incoming airflow less drafty and more controllable. Plus, shading devices like blinds or louvers can be integrated and protected within this cavity.
So it's like a pre-treatment zone for the air.
Sort of, yes. The GFW building in Berlin is cited as an example where the double facade cavity itself is designed to facilitate cross-ventilation through a stack effect occurring within the facade depth.
Wow. And the cutting edge involves adaptive or smart skins.
That's the goal. A facade that can physically change how it operates based on real-time conditions. Maybe windows that adjust their opening angle or direction, depending on wind speed or direction. Research is exploring things like reactive materials.
Materials that move on their own.
Potentially, like bimetal strips that bend in response to temperature changes, solar radiation, or even wind pressure, triggering an opening or closing action. Or kinetic architecture, where parts of the facade literally move. While some kinetic facades are more about visually representing wind, research is definitely exploring how dynamic elements and even manipulating surface roughness at openings using balconies, overhangs, recesses, material textures can influence and control airflow locally.
It's clear architects have an increasingly sophisticated toolkit then, drawing on both ancient wisdom and new technology to shape how air moves. And these design choices directly impact occupant comfort, air quality, and, of course, energy use.
Fundamentally. But beyond the physics and the design diagrams, ultimately, natural ventilation is about us, the human element, how we experience comfort, how we interact with our environment, and how we live with natural air.
And the source delves into how our understanding of thermal comfort really changed dramatically with the widespread introduction of air conditioning. Suddenly, the expectation shifted, didn't it?
It really did. The expectation became those homogeneous and constant interior thermal conditions that perfectly uniform, predictable temperature, usually a narrow band around, say, 72 degrees Fahrenheit or 22 Celsius.
And the availability of relatively cheap, consistent comfort through AC maybe made people forget, or engineers overlook, that simply opening a window could provide perfectly comfortable conditions for much of the year in many climates.
Exactly. Engineering standards focused heavily on maintaining these very tight temperature ranges, which often led to buildings being designed with sealed envelopes and no operable windows, prioritizing energy-intensive mechanical control over simpler, passive, natural solutions. Designing for low-energy comfort often got overlooked in the early design stages.
But research is pushing back against that narrow definition of comfort now, right? With the adaptive thermal comfort model.
Yes, this model, which is now incorporated into major standards like HHRE Standard 55, offers a more dynamic and realistic approach.
How does it work?
It acknowledges that people are adaptable. Our perception of comfort isn't just about the number on the thermostat. It relates to the outdoor climate we're experiencing, the clothes we choose to wear, and our expectations.
So we tolerate warmer temperatures in summer.
Generally, yes. Studies like those by Didier and Braiger cited in the source show convincingly that occupants in naturally ventilated buildings are comfortable across a significantly wider range of temperatures than people in tightly controlled, air-conditioned spaces where expectations are different. The adaptive standard reflects this, allowing acceptable indoor temperatures to float more widely, tracking outdoor conditions seasonally. It requires indoor conditions to change with the outdoor climate.
This connects beautifully to Lisa Heschong's wonderful concept of thermal delight in architecture.
Oh, her work is fantastic. It's unique because it focuses on the qualitative, the sensory experience of thermal comfort, the actual feeling of being warm, cool, airy, or cozy. It's about delighting in thermal variation, not just striving for bland neutrality.
Like the pleasure of sitting by a warm fireplace on a cold day.
Exactly. Or relaxing on a breezy porch swing in the summer heat. Those are moments of thermal delight.
And she points out how these thermal experiences were often linked to social life, didn't she? That classic image of porch culture in parts of the U.S.
Yeah, where people would gather outside in the evenings, interacting with neighbors, passively supervising the street. A lot of that faded when AC drew everyone inside into their sealed uniform boxes. Our language even reflects this connection. Words like snug or airy inherently describe a feeling of thermal well-being often derived from naturally conditioned spaces.
Our own bodies play a big role too, our physiology, our metabolic rate.
Right, the energy our bodies produce just by being alive and doing things. It's measured in MET-Ts. One MET is the heat produced by a person sitting quietly, roughly 100 watts. But if you're exercising vigorously,
You produce way more heat.
maybe 5 times as much heat or even more. And someone producing 5 times the heat needs much cooler conditions or significantly more airflow, like from a fan or an open window, to feel comfortable compared to someone sitting still. That increased air movement helps cool the body through convection and increased evaporation of sweat.
And standard comfort models struggle to account for these dynamic changes in individual activity levels within a space.
They do. It's a challenge. This raises a really interesting and increasingly relevant question, especially with climate change concerns. How warm can we let spaces get in naturally ventilated buildings and still have them be considered comfortable and productive?
The source notes this kind of flips the historical debate about the onset of air conditioning. Now we're thinking about the upper limits of acceptability for sustainability. It even touches on Huntington's provocative, though maybe a controversial idea from decades ago.
That the very uniformity brought by AC might have seriously impaired human achievements by removing the need for environmental adaptation.
Yeah, that idea. The answer to how warm is too warm is still being researched and debated, and likely varies by culture and expectation.
And making natural ventilation work well in practice also means tackling some very practical challenges for both designers and the people using the building.
The acoustic seems like a big one.
Definitely. If your fresh air inlets are facing a noisy street, that sound comes right in with the air. Also, hard surfaces inside, like exposed concrete used for thermal mass, can make spaces acoustically live or louder.
So what can designers do?
They need strategies. Careful placement of openings away from major noise sources. Using sound-attenuating components within the vents themselves. Incorporating sound-absorbing materials inside the space. Even using landscaping berms, dense planting outside near inlets can help buffer noise.
What about fire safety, especially in those open-plan, free-flow spaces?
Critical concern. Buildings with large, open volumes that encourage airflow, like atria, need specific fire and smoke control systems. Things like smoke curtains, dedicated exhaust systems. The Unilever house in Hamburg is mentioned as an example needing such protective elements.
And then there are the basics, security and privacy with operable windows.
Always practical considerations. How easily can someone access the building through an open vent? How much can people see in or out? These need careful detailing and design choices.
And just dealing with the weather, rain, snow, high winds.
Right. You need effective control systems, even if they're simple on-off modes, to manage when openings can safely be used based on external weather conditions. You don't want rain pouring in through your ventilation opening.
Which brings us to control systems themselves.
Even simple controls need careful design. Sensor placement is absolutely critical. You don't want a temperature sensor sitting in direct sunlight or right next to a piece of heat-generating equipment because it will give a false reading and might close the vents when you still want cooling.
So you might use schedules or occupancy sensors instead sometimes.
Those are alternatives. Yes, if ideal sensor placement isn't feasible or reliable, controls can range from fully automated systems to simple manual overrides for occupants.
Okay, one really powerful strategy that leverages both thermal mass and natural ventilation is night flush cooling. Can you break that down?
Sure, this is a key passive cooling technique, especially effective in climates with significant day-night temperature swings. It relies on using the building's structure itself to store coolness.
How does that work?
The heavy parts of the building, exposed concrete floors or walls, maybe phase change materials, PCMs, embedded in the structure, these have high thermal mass. They absorb heat gains from occupants, lights, equipment, and sunlight throughout the day, soaking it up slowly.
So the mass gets warm during the day.
Right. Then, at night, when the outside air temperature drops significantly, the building is ventilated, often at higher airflow rates than during the day, using natural ventilation openings or sometimes low-energy fans.
And this cool night air flows over the warm structure.
Exactly. It flows through the space and directly contacts the warm thermal mass, cooling it down overnight. The structure essentially gets recharged with coolness. It acts like a thermal battery.
So the next day.
The next day, as heat gains start again, the cooled mass slowly absorbs that heat, preventing the indoor air temperature from rising quickly. It delays and reduces the peak cooling need until the mass becomes saturated with heat again.
That sounds really effective.
It can be extremely effective. The Paul Wunderlich House is cited as a great case study. They found that night ventilation provided close to 50% of the building's total cooling energy needs.
Wow, half the cooling load.
Yes, but it requires an integrated design approach, a very airtight building envelope to prevent unwanted heat gain loss, significant exposed thermal mass, concrete in this case, phase change materials to boost storage capacity, and it was supported by ground source heat pumps for the remaining load. It demonstrates how powerful working with natural cycles can be.
So comfort in a naturally ventilated building is clearly different. It's subjective, it's adaptive, it's connected to the outside world. It offers a potentially richer thermal experience, something that can be genuinely delightful, but making it work reliably requires addressing practical challenges like noise, security, and control through really thoughtful design.
Absolutely. And to bring all these complex ideas together, the physics, the climate, the building form, the human factors, and actually predict how a specific building design will perform with natural ventilation, designers need tools. They need ways to quantify the breeze, essentially.
This need to predict performance under dynamic outside conditions seems crucial. The source mentions this was actually what sparked the decade-long research effort that led to the book we're referencing. Architects wanted a way to really understand and quantify how their spatial design choices impacted airflow.
Exactly. Predicting performance is challenging because the driving forces wind and temperature are constantly changing. Historically, some approaches used simpler empirical models.
Based on experiments.
Yes, models based on experimental data, like those mentioned by Shaw and Loomis or Larson and Heiselberg. They provide empirical relationships, formulas, linking airflow rates to wind speed, or temperature differences based on measurements in wind tunnels or actual buildings.
What's the limitation there?
The main limitation is that the constants and relationships in these models can be very specific to the particular building geometry, opening types, or urban environment where the experiments were conducted. They might not be accurately transferable to a very different building design.
But what's the state-of-the-art tool now?
Today, a much more powerful and widely used tool is computational fluid dynamics, or CFD.
Okay, CFD. Sounds complex.
It is complex computationally, but the concept is understandable. Think of CFD as a virtual wind tunnel combined with a thermal analysis tool running on a computer.
How does it work?
You start by building a 3D digital model of the building and its immediate surroundings. Then you need to set up the simulation. This involves defining a computational domain, the volume of air you want to simulate, and dividing that volume into a grid, or mesh, of many small cells. The detail of this mesh, coarse or high resolution, affects accuracy and computation time.
And then you tell the software about the condition.
Yes, you define boundary conditions. For solid surfaces like walls and floors, you typically use the standard no-slip boundary condition, meaning the air velocity right at the surface is 0. For openings like windows or vents, the boundary conditions depend on what's driving the flow. You might prescribe a wind velocity profile if it's wind-driven, or maybe just the ambient outside pressure and temperature if the flow through the opening is unknown or driven by buoyancy.
And the software calculates the flow.
Essentially, yes. It solves a set of complex mathematical equations, like the Navier-Stokes equations which govern fluid motion for each cell in the mesh. This allows us to calculate the air velocity, pressure, and temperature throughout the entire simulated space. You can then visualize these results as airflow patterns, temperature contours, pressure maps, etc.
And you can get numbers out of it, metrics.
Absolutely. CFD allows calculation of key performance metrics. A very common one is air changes per hour, or ACH. This tells you, on average, how many times the entire volume of air in a specific room or zone is replaced with fresh outside air in 1 hour.
And CFD can show how different strategies affect ACH.
Dramatically, it can clearly show the difference. For instance, simple buoyancy-driven stack effect alone might only give you relatively low ACH values, maybe around 1 ACH, which might be just enough to meet minimum fresh air requirements for occupants, like ASHRA's baseline of 0.35 ACH.
But wind-driven flow.
Wind-driven cross-ventilation, simulated with CFD, can often achieve much, much higher ACH rates, maybe 12 ACH, 50 ACH, even over 100 ACH in some cases, depending on wind speed and opening sizes. These higher rates are far more effective for removing heat quickly and providing a strong sensation of cooling airflow, meeting higher recommendations for heat removal, like RABA's 215 ACH.
Can CFD look at turbulence and buoyancy too?
Yes. It uses turbulence models to simulate the effects of turbulent flow, and dimensionless numbers calculated from the results can help characterize the flow. The Reynolds number indicates whether the flow is likely to be laminar or turbulent. Numbers like the Grashof or Rayleigh number indicate the relative importance of buoyancy forces and whether buoyancy-driven flow itself might become turbulent.
Can it simulate changes over time?
Yes, you can run transient simulations that show how airflow patterns evolve over time, reacting to changing wind or temperature inputs. This involves calculating the flow at small time steps, often estimated using concepts like the current Friedrichs-Lewis CFL number to ensure stability.
So while it might seem like complex math behind the scenes, CFD gives designers a powerful way to test strategies virtually.
Exactly. Modeling helps designers test different opening configurations, different building forms, understand how their choices translate into actual airflow and ventilation performance, and ultimately helps ensure the building doesn't just look good on paper, but also feels good and provides a healthy environment inside. It reduces guesswork.
Okay, so we've covered a lot of ground in this deep dive. We went from that basic, ancient, fundamental need for fresh air
And the basic physics that makes air move wind and buoyancy.
through architectural history, the wisdom in vernacular design, the unique challenges of the urban environment.
To the sophisticated modern design strategies being used today, from cross-ventilation to adaptive facades.
We touched on the nuances of how we actually experience thermal comfort, the adaptive model, thermal delight.
And finally, the science of modeling and prediction with tools like CFD.
It's really clear that natural ventilation, when done well, is this sophisticated blend of art and science. It's absolutely crucial for health, for energy efficiency, and just for creating spaces that feel genuinely responsive and pleasant to be in.
It really requires understanding the natural forces available on a specific site, the patterns of wind, the potential for stack effect based on temperature and designing with them, shaping the building's form, its openings, its materials to collaborate with those forces, rather than just trying to fight against the outside world with brute force mechanical systems.
And as the source material explores that fascinating shift in how we think about thermal comfort highlighting our adaptability, the concept of thermal delight, it offers such a compelling contrast, doesn't it? Between the uniform, often sterile conditions air conditioning strives for, and the dynamic, variable, connected experience natural ventilation can provide.
It really does.
Considering how incredibly adaptable the human body actually is, and the genuine delight that can come from those varied thermal experiences, the feeling of a warm patch of sun on your skin in a cool room, the sudden cool rush of air from an open window, it does leave you with a thought, doesn't it?
What's that?
Could designing spaces that intentionally connect us back to the outside world, spaces that respond dynamically to climate rather than sealing us off in a bubble, could that unlock not just massive energy savings, but actually a richer, more sensory, and perhaps even more delightful way for us to inhabit our buildings? It's definitely something to ponder the next time you feel that perfect breeze indoors.